Hello, today I will consider all the problems which was proposed at the EGMO 2024. The EGMO is the European Girl Mathematical Olympiad. In the first problem, this was from algebra part, and we are given two numbers, u and v, which are written on the board, and we can make two operations. Either we can add these two numbers, instead of a and b, write a plus b, or if x is the root of this equation, ax squared plus bx plus c equal to 0, then x can be written on the board. And the question was to find every pairs of u and v such that from this pair we can generate all integers in a finite number of steps. For the first step, at least notice that if u and v are both negative numbers, after applying the first step, u plus v, this will be also negative. And by using first steps, we cannot get any positive integer. And if you look at the second operation, ax squared plus bx plus c, this cannot have any positive root. And why it's correct? If x is greater than 0, a times x squared, this is less than 0, b times x is also less than 0, and c is also less than 0. So their sum would be negative and cannot be equal to 0. So if both u and v are negative numbers, we cannot generate any positive integer. So this is one restricted pair. Now let's consider the case when we got 0 and something. If we are given v equals 0 and use any number, by applying the first step, we cannot generate any new number. So we are getting only u and 0 written on the board, and we can't also use the second operation because we don't have three distinct numbers. So this is also a restricted pair. And now let's consider the last pair which is restricted, and this is 1 and negative 1. By applying the first operation, we can generate 0, but after applying the second operation, we cannot add any integer because ax squared plus bx plus c does not have any root which was not before, after choosing a, b, and c from this set. So we can see that 1 and negative 1 is also a bad pair. And now we will show that every other pair would be good. For example, if we take u and v both positive numbers, we can take u plus v from them, plus v. And now we use the fact that if we take x equals negative 1, this is a minus b plus c equal to 0. And instead of b, we can take just u plus v, and for a, we can take u, and for c, we can take v. And this means that if we are given u and v, we can generate negative 1. And because u and v are positive numbers, we can take any large enough integer by u times kv operations if we apply addition of v multiple times. And if we make this negative 1 operation to this number, we can generate every number which is less than every integer which is less than u plus k times v. Clearly, this such pair works. And now consider the case when one number is greater than 0 and greater than 1 itself, and the second number is less than 0. If u is greater than 1 and v is 0, by using this operation, we can also generate negative 1. Negative 1 can be also written on the board, and because u is greater than 1, u plus negative 1, this would be positive number. And now we get back to the previous case when we got two positive numbers written on the board, and if we apply the same argument, we will get that we can generate every integers. And now consider the case when we got u equals 1 and v is negative number. If we use the same operation, we can take negative 1, x equals to negative 1. And also, because v is less or equal to -2, we can take every negative number. Like if we just add 1, we can generate number -2 on the board. And if we write the x squared minus ax minus 2, this equation has one root, x equals to 2. So we have written 1 and 2 on the board, and if we apply the argument which was taken here, we will see that we can generate every number. So the number of good pairs will be everything which are not in this region. Then u and 0, 1, -1, and u and v both negative numbers. This was everything what I wanted to say about the first problem. If you got any questions, write in the comments. The second problem was given from the geometry part. We are given an ABC triangle with AC greater than AB, and omega is its circumcycle, while I is the incenter. Insert incenter tangents to the AC, BC, and AB in EDF respectively, and X and Y are chosen on FD and ED arc such that BXD angle equals DYC angle. And if we take the intersection of XY and BC, call this point K, take the tangent from K to omega cycle T, then we want to show that TD and AI intersect on the circumcycle. So because we know that AI intersects in the midpoint of the arc BC, our aim is to show that DT and midpoint of arc BC are collinear. To show this, the first step is to notice that BXYC is cyclic. Now we use our given statement that BXD equals some alpha and DYC is also alpha. If we use the tangency formula, angle XDB equals angle XYD. So this would be also beta. And if we want to compute the angle XBD, this would be 180 minus alpha minus beta. Now let's look at the angle XBD plus angle XYC. This would be 180 minus alpha minus beta plus alpha plus beta. And clearly this is 180. This means that BXYC is 6. Because K is the intersection of XY and BC, we can say that power point of K times B times KB times KC equals KXY, KX times KY. Now use the fact that D is the tangency point of in-cycle and BC line, so KX times KY, this must be equal to KD square, while KB times KC must be equal to KT square. So we got that KT square equals to KD square. So KT is similar, congruent to KD. So angle KTD equals to angle TDK. And now use the fact that, call this point L, angle KTD is half of arc TL. So this is half of arc TC plus LC. TC plus LC over 2. While angle TDC or TDK, they are same. TDK is half of arc TC plus arc BL. So we get that by using these two equations that LC arc equals LB arc. So this means that L is the midpoint of arc BC, and this is what we wanted to show because AI passed through the L and TD also passed through the L. If you got any questions, write in the comments. That problem was from the number theory section. In this problem, we are calling a number n peculiar if for every positive divisor of n, d d times d plus 1 divides n times n plus 1. And we wanted to show that if we take any four different peculiar numbers, their GCD would be 1. And now we will show what kind of numbers are peculiar. Clearly, if n is prime number, this is peculiar number because it has only two divisors, 1 and p, and 1 times 2 divides p times p plus 1. And p times p plus 1 clearly divides p times p plus 1. So every prime number is peculiar. And now let's take a number if it has more than two divisors. And now if we take n p1 to the alpha 1, p2 to the alpha 2, and so on, pk to the alpha k. P1 is less than P2 and so on. Take n over P1. This must be also a divisor of n, and this would be the greatest divisor. N over P1 times n over P1 plus 1. This divides n times n plus 1. So we will get that n over P1 plus 1. This divides P1 times n plus 1. Now we have to consider several cases here. If n is also multiple of P1 square, if this happens, from here we can conclude that n over P1, this is also a multiple of P1. So GCD of n over P1 plus 1 and P1, this would be 1. So we can conclude that n over P1 plus 1, this divides n plus 1. Now if we use the Euclidean algorithm and take P1 times this number, this divides n plus P1. So n plus P1 and n plus 1 both are divisible by this number called this t. So their difference is also divisible by t. So P1 minus 1 is divisible by t, and t is n over P1 plus 1. And this number is greater than P1 because n was multiple of P1. And clearly this is contradiction. So n cannot be a multiple of P1 squared. Also, P1 must be a divisor of n over P1 plus 1. Otherwise, n over P1 plus 1 cannot divide n plus 1, just n plus 1, if we erase the P1. So we can take n over P1 plus 1. This number divides n plus P1. Now, if we apply the Euclidean algorithm once again, we will see that if n over P1 plus 1 divides n plus 1, n plus P1, and this must also divide n plus 1, clearly this means that these divides their difference, and their difference is P1 minus 1. So the GCD between n over P1 plus 1 and n plus 1 is also GCD of n over P plus 1 and P minus 1. So we will get that n over P1 plus 1, this divides P1 times P1 minus 1. Clearly we can see that if n has more than two divisors, like P, two prime divisors, P, Q, and R. Clearly Q and R are greater than P, and n over P1 is at least Q times R, and Q times R is greater than P1 times P minus 1. So this is impossible. So n has at most two prime divisors, so P and P1 and Q. And we cannot have any perfect square, like perfect square cannot divide n. So this is square free, because if q square divides n over p1, this would be greater or equal to q square, which is greater than p1 times p1 minus 1. Contradiction. So n is exactly p times q, or q times p. What do we know about q? Is like q plus 1 divides p1 times divide p1 times p1 minus 1. Now let's look at the case. If q plus 1 is not multiple of p1, this means that q plus 1 divides p minus 1. But this is contradiction, because q plus 1 is greater than p1 minus 1. So p1 plus 1 is divisible by p1. And now, what will we get if we choose divisor p? So p times p plus 1 must divide pq times pq plus 1. Let's erase p. So we will get that p plus 1 divides q times pq plus 1. But we know that q plus 1 cannot divide q, because q is prime number and p plus 1 is less than q. Equality can't hold if we don't consider the case 2 and 3. And this case can be eliminated very easily. So p plus 1 divides pq plus 1. And what does this mean? P plus 1 divides pq plus q. So from here, by using Euclidean algorithm for pq plus q, we can see that p plus 1 divides q minus 1. So we are given two equations. P plus 1 divides q minus 1, and p1 divides q1 plus 1. So this is p1. p1 and p are same numbers. So p1 equals p. Avoid any confusion. Now we are searching for the prime number, which equals q equals 1 mod p plus 1, and q1 q equals negative 1 mod p. So we can consider q as k times p1 p plus 1 plus 1. So this is kp plus k plus 1. And this number must be negative 1 mod p. So we can see that k must be just p minus 2, because we cannot take any number which is greater than p. And if we take k p minus 2, we get that q equals p square minus 2p plus p minus 2 plus 1. And this is just p square minus p minus 1. So we have shown that every peculiar number is p times q. There, between p and q is this connection. Q must be represented as p square minus p minus 1. And so we can see that every prime number can be also divisor of at most 3 peculiar numbers. So this is impossible for the 4 numbers to be their GCD greater than 1, because this prime number must have 4 peculiar numbers, and this is impossible. If you got any questions, write in the comments. This was the end of the first day. The first problem of the second day was from combinatorics. If we are given a sequence of n integers, a1 is less than a2 and so on, it is less than an, we call a pair of integers ai and aj interesting if they exist another pair of integers k and l such that AL minus AK over AJ minus AI equals 2. And the question was to find largest possible number of interesting pairs in every sequence of n numbers. We used to show that this sequence to consider all powers of 2, 0, 1, 2, all the way up to 2 to the n minus 1. If we take 2 to the I minus 2 to the j over 2 to the I minus 1 minus 2 to the j minus 1, this pair is always 2. So we can see that every pair, there we don't have 2 to the n minus 1. We can always find the term of another pair for which this equation equals to 2. And for 2 to the n minus 1, if we consider 2 to the n minus 1 minus 2 to the n minus 2, and 0 and 2 to the n minus 1, this would be exactly 2. So what would be the final answer from this? This would be n minus 1 choose 2 plus 1, because we can choose two numbers from the first n minus 1 indexes and one number for this. And now we will see that this is the more optimal answer. In total, we have n choose 2 pairs. And if we show that we have to subtract at least n minus 2 numbers, this will prove that this is optimal number. And now, if we consider every index I and pairs 1, I, and ni, let's call an minus a1 this number be n. Clearly, m is the greatest number. And if we got any number which is greater than m over 2, this pair cannot be interesting. And now we will see that at least one of these numbers, 1i or ni, would not be interesting because they would be more than half. And why it is correct? Because ai minus 1 minus a1 or an minus a1 is greater than m over 2. Otherwise, their sum cannot be equal to m. And if equality happens somewhere, this number would be at most 1 because these numbers be sorted. So we can say that at least n minus 2 indexes would be uninteresting because there can be equality only just 1. So this means that we have to subtract at least n minus 2 bad pairs out of n choose 2, and this would be n minus 1 choose 2 plus 1, and the construction was what I have done in the first step. So if you got any questions, write in the comments. The second problem of the second day was from number theory. This was functional number theory, which most of the cases are very similar to each other. We are given function from positive integers to positive integers, and we know that x and f of x has the same number of positive divisors. And if we know that x does not divide y and y does not divide x, GCD of x, fx, and fy is greater than f of GCD x and y. And now we will show that f of x would be some prime number q to the number of divisors of x minus 1 power. At first, it's easy to notice that f of 1 is 1 because 1 does not have any prime divisor, and f of 1 must not have any divisors except 1. So f of 1 is 1. And what can we say about f of p? F of p is some prime number q because p has only two divisors, 1 and p itself. and q must have also two divisors, 1 and q. And if we take the second prime, f of p2, we will show that this must be also same prime q. Otherwise, if we consider the GCD of fp1 and fp2, we will see that this must be greater than 1. Because p1, this is q, and this has only 1 and q, its divisors, f of p2 must be also q. Otherwise, their GCD would be 1, and clearly this is impossible. So f of p2 is also q. Now we will show that f of p to the n, this is also q to the n. And to show this, we will use induction. At first, notice that GCD of fp1 square and fp2, this must be greater than 1. But we know that this is q. So fp1 square is also a multiple of q. So we will get that f of p1 square, this is divided by q. But we know that p1 square has just 3 divisors, so this means that fp1 square must be q square. And now let's consider the case if we take f of p times r. Where p and r are different prime divisors. We will show that this is also same as this must be q cubed. To show this, we need to use the second proposition. If we consider GCD of f of pr, p1r, and f of p2r, or p1 square, it's better to take p1 square, this is greater than f of p1. So this is greater than q. But we know that this is q square. So this means that f of p1r is also multiple of q square. But we know that f of p1r is multiple of q square, and it must have exactly 4 divisors. So this must be equal q cubed. Otherwise, this will have more divisors. So if p1r is q cubed. And now by induction, if we substitute f of GCD of f, f of f to the p to the n and f of p to the n minus 2 and r, some r, this must be greater than f of pn minus p minus 2, which is q to the n minus 2. So this means that this number is, clearly we know that this number is q to the n minus 1 times 2 times minus 1 because of induction. And f of p to the n must be also a multiple of q. And this number must have at least, not at least, exactly n divisors. So this is also q to the n. So we have proved that f of p to the n is q to the n. And similarly, we can show that f of p to the a times q to the b minus a, like b, this would be, no, this can be any q. Like if we take two different prime divisors, so p1 to the alpha 1 and p2 to the alpha 2, we would get that f of p1 to the alpha 1, p2 to the alpha 2, this would be q to the alpha 1 plus 1 times alpha 2 plus 1 with minus 1. And we will prove this by induction. Now let's assume that we have proved this for k different prime divisors and then show that for k plus 1 the formula would be same. So let's just take f of p1 to the alpha 1, p2 to the alpha 2, pk to the alpha k. This would be q to the alpha 1 plus 1 times alpha 2 plus 1, alpha k plus 1 minus 1. And now show that what would happen if we add some small number r. Now show that this is correct for every r. P1 to the alpha 1, pk to the alpha k, and r to the any power, x power. Now we relieve the fact that if we know this for p1 to the alpha 1, pk to the alpha k, times r to the x minus 1. So we are making an induction for the power of r. And clearly, power of r would be 0 in the beginning, and then we will show for 1, 2, and so on. For this, let's consider the GCD of f of p1 alpha 1, p k alpha k times r to the x, and second number would be f of p1 to the alpha 1 plus 1, p2 to the alpha 2 plus 1, and so on, pk to the alpha k plus 1, r to the x minus 1. Then their GCD must be greater than this number, because their GCD is p1 to the alpha 1, p2 to the alpha 2, and r to the x minus 1. And by the induction, we know that this is q to the alpha 1 plus 1, alpha 2 plus 1, alpha k plus 1 times x minus 1. So we can see that this number, f of p1 to the alpha 1, pk to the alpha k, times r of x, like r to the x, this is divisible by q to the this number, because we can see that right hand, like this number is only multiple of q. And how can we show that this doesn't have any other prime divisors? So number of its divisors is alpha 1 plus 1 times alpha 2 plus 1, so the last one, this would be x plus 1. And now we will show that this is less than 2 times this number. And clearly this is correct. So this would be alpha 1 plus 1 times alpha 2 plus 1, this would be x, and final minus 1. And this will be correct. So this means that if we add new prime in f of p1 to the alpha 1, pk to the alpha k times r to the x, this new prime number t, call this t will contribute by at least 2 in the number of divisor formula. And clearly this will give us the contradiction. So we will prove that for every number f of p1 to the p1 to the alpha 1, so up to pk to the alpha k times r to the x, this has only one prime divisor, and this divisor is q, which was the before, and we have to take q to the alpha 1 plus 1, alpha 2 plus 1, and so on, is x plus 1 minus 1. X plus 1 minus 1. Because this must have the same number of positive divisors as p1 and alpha 1 up to r to the x. And now we are checking the answer. Clearly, x and fx has same number of positive divisors, and if we know that x does not divide y and y does not divide x, GCD of x and f of x and f of y, this would be clearly greater than GCD of f of GCD of x and y. And this was all I wanted to say with this problem. If you got any questions, write in the comments. Now it's time for the last problem at the EGMO. This was third on the second day, so this was algebra problem about polynomial. This was very hard problem, and if you think that I will prove this in this video, you missed very much, because this will demand a lot of work, and I will present you a solution of this problem if this video will take at least 50 likes. Now I will discuss the levels of the problems. In my opinion, third problem was easy for its position. Second problem was also easy for its position, and the first one was a bit hard for its position, because they have to consider a lot of cases, and it was easy to lose some points. In my opinion, first day was very easy, even for the EGMO, and second day was very hard for the EGMO, because problem 4 demand some caseworks, and it was not easy to find the construction and then bounding. That's why most of the students, maybe more than half of the students, could not solve this problem. Problem 5 was very original, like there are too many problems like this in the Olympiad, so if you are experienced, you will solve them maybe in at most 1 hour. And problem 6 was very hard. So if we look at the scorings, and the scoring was 33 points was gold, so it wasn't hard to take gold if you solve first 5 problems. And for silver, 25 score was silver, and I think if you want to take at least silver, it is better to take at least 18 points for the first day, maybe some loose points for the first or third. Like second problem was very easy to notice that bxyc was cyclic, and then use the fact that power of points. So if you like this video, don't forget to like and subscribe if you want to see the solution of this problem.